Right, let's take a look at a worked example. So up here we've got our centre of mass. You can see here I've chosen a nice simple object, but we've got a chosen point. Okay, centre of mass problems are always relative to something. So it'll be relative to the end of the rod, or relative to where John is standing, relative to something. Centre of mass doesn't exist in a vacuum. It's not something we can talk about this way mathematically without having a system, a surrounding around it. So we can talk about the centre of mass of an object. So a ruler has a centre of mass. We only know that because we are holding it, okay? Because we've done something, we've interacted with it some way. So all mathematical problems will ask you relative to somewhere when you're calculating it. Now, of course, you don't have to calculate the centre of mass. You can just get the object, if it's a real thing that exists, get the object and hold it until it becomes steady. That's not always very practical, though, which is why we have a mathematical approach. But that's a real life situation. So here's our object here. It's got two masses and it's got a chosen point, which is outside those two masses. So we can see, we've said it's mass 1, there's the distance to mass 1, mass 2, there's the distance to mass 2. And our mass is really simple, okay? Our mass says that the position of the centre of mass compared to our point is going to be the mass times the distance plus the other mass times the distance divided by the total mass. This gives some weighting to the mass. So if the two masses are the same, obviously this is going to work out so those masses cancel out and the centre of mass is in the middle. On the other hand, if the masses are different, the larger of the two masses will weight the centre of mass more towards one end than another. Now, if we're talking about a system which has more than two components, we can write it in this form, okay, which uses the Greek letter sigma for sums. Now, I don't know if you've done sums before, but the idea is that when you see a sigma, you're summing all the things in the series, in the sequence of events. So we've got the sum of the masses and distances divided by the sum of the masses, okay? It's relatively straightforward maths as long as you don't get like perplexed about this relative to business. So here's an example. I hope you can see the green okay, but our example is a large mobile, an artwork, an installation, and it's got a very big rod of some kind, and we can see this here down the bottom. This rod is 2.4 metres long from our chosen point to the end. And we're saying, well, if our mobile has a mass hanging on the end, where is the centre of mass of our system? We've got a rod. We know where the centre of mass is for that because it's a uniform object. We have a weight of some kind of decorative, artistic thing. And we're saying, well, where is the centre of mass compared to the other end of the rod? So this is our chosen point. We're going to look for x along this distance here, a distance x from the chosen point to somewhere. Now, we know that it's going to be closer to 2.4 metres than it is to 0 metres. We know it's going to be more down this end. And we know that just by using our instinct for physical systems. If we've got something that's light at one end and heavy at the other end, the centre of mass will be towards the heavy end. But let's do some maths. So, as with all mathematical problems in physics, we write down what we know. And I've written that on the diagram. We then write down the formula we're going to use. We substitute in the numbers that we have, we solve it, and we check that it's a likely solution, or we check for traps. So in our case, we've said, well, the bar first, 5 kilograms times 1.2, the distance from our reference point to the centre of mass of the bar, plus 7 times 2.4, the mass of our decorative item, times the distance from our reference point, all divided by 5 plus 7, the two masses. And that works out to be 1.9. which is, as we predicted, closer to the heavy end of our decorative object. So we've done some maths and it worked out accurately. We're happy.